Hi, everyone. It's Marley with the MacMillan Space Centre. This is just me today. Michael is on vacation, just like I was on vacation a few weeks ago. So we are just splitting up the duties. So today it is just me. Those of you on YouTube, hello. And those of you also out there on Telus Optic, hi. Today, I am going to be talking about two new stories. Well, one less new and one very new as of kind of last night and this morning, all about the Comet Leonard, which you may have heard of in the past few days, and also about a new planet, a new exoplanet that has been discovered. So I'll share my screen and then we can get going. And hopefully you can hear me okay. I have a new fancy lapel mic, so hopefully that's working as well. Say in the chat if it's not, and I will fix it. So here we go. A new planet and a new comet that's been discovered. So I wanted to start with the new planet because I thought ending off with how you could see Comet Leonard would be a good place to end today. So this new planet, this is a picture of it, and it is orbiting around a pair of stars, a stellar pair. The star pair's total mass is at least 6 times that of the sun, at minimum, that much mass. And in this image, the bright and dark rings around are just optical artifacts. They're not actually part of the star at all. So the planet is noted by the arrow in this image in the bottom right-hand corner, and the planet itself is estimated to be about 10 times the mass of Jupiter, and it orbits around 100 times the distance Jupiter orbits our sun. And that is very, very interesting. This was not something astronomers had in mind when they were doing or anticipated when doing planetary evolution and planetary formation. Having a star of this type with this large of a planet at this distance was not something that was anticipated. So in this image as well, you'll notice 2 other spots on the image. Those are background stars. And the way astronomers were able to tell that these were background stars is because they looked at data and took data over large periods of time. And they noticed that the planet moved and changed position, but the stars did not. So they were able to determine that those were just background stars. This image comes from the specific instrument, the SPHERE instrument from the European Southern Observatory's Very Large Telescope, or VLT, and it used a coronagraph to get this image. And the coronagraph blocks out the light from the parent star or the star system and lets astronomers detect the much, much fainter planet. And prior to this, astronomers had not found a planet this size orbiting around a star that was more than 3 times the mass of the sun. So previously, we did see planets this size, this distance or so, but they were always around stars that were 3 times the mass of the sun at most. And so we assumed that that was the absolute limit that these planets could form around. Unfortunately, we will never actually see the constellation that this lives in because it is in the Centaurus constellation, which is in the southern hemisphere. It never sets in the southern hemisphere, so it never rises here. And the star system itself is not Beta Centauri. It is B Centauri or B Cen or HR 5471. Or HIP 71865. So it's the star in this diagram that's circled in with the red circle. That's where the actual star is. And this map shows most of the stars that would be visible to the unaided eye under good conditions. So the system would be able to see under good conditions with the unaided eye, just not where we live. What's interesting about the star system and the stars in particular are really the stars themselves. So it's made out of 2 stars. There is a more massive star, which they call the main star or the primary star, and it's named B Cen A, lowercase b Cen capital A. And it is of spectral type B. And so spectral types are a way astronomers gather information about the star's temperature. And so in a spectral class B star, they tend to be blue or lighter blue, and they're very, very hot. In this case, this specific star has an effective temperature of about 18,000 Kelvin. So it's very, very hot, much hotter than our sun. The second star, which is called lowercase b, Sen capital B, is only known through its influence on A. They've never actually seen it, but they know it's there. And there's no full orbital characterization of the system, and its properties are uncertain because of that. What the scientists do think, based on all the math and all of the elements and things going on there, is that the system itself has a lower limit on the mass of 6 times the mass of the sun and a upper limit of 10 times the mass of the sun. So either way, the system itself has a lot of mass, more than they were expecting to see. The planet itself is denoted as B Sen ABB, and AB just denotes that it orbits both the A and B star. So it doesn't orbit one of them, it orbits the 2 of them at the same time. And the thing about the main star is that we know what type of star it is, and so they can study it and there's more information about it. Being spectral class B, it's about 3 times as hot as the sun. And since it has such an intense temperature, it emits large amounts of ultraviolet and X-ray radiation, very energetic things happening and lots of damaging radiation. And so what was thought is that the mass and heat from this type of star was known it has a strong impact on surrounding gas. And what it does, like the hotter the star, the more of a higher energy radiation you'll produce, those X-rays and UV rays, and that makes the surrounding material evaporate faster. So when planets form, they form what's called a protoplanetary disk, which is a disk of gas and dust that orbits a star. And so if a star has a lot of ultraviolet and X-ray and high energy radiation, it would cause all of that dust and gas to evaporate faster than perhaps a planet could form. So this is why scientists believe that it would be difficult for very large planets to form around these types of stars, which is why finding this planet around this star system is so interesting and so exciting. It is actually causing scientists to kind of rethink how planetary evolution happens and how it happens around larger stars. And a fun fact is that in doing their investigation and the research into this system, the team actually went through archival data as well. And so the planet was actually imaged before, more than 20 years ago. There's actually a photo and data of it taken by the European Southern Observatory's 3.6 meter telescope. But at that point, it was not recognized as a planet at all. Oh, thanks, Michael says, I am sounding great. Oh, Michael's tuning in. Everyone say hi to Michael while he's here. But it was not recognized as a planet. So this actually offers a lot of interesting tangential questions, especially getting into the search for exoplanets and places otherwise. So this is a figure from the paper where that was published just last night / early this morning. And it shows a lot of things. So I'm going to try to go through and kind of explain it. The green, so there's 5 different ways to detect an exoplanet. And 4 of these ways have been plotted on this graph. So green are transit detections, which is when the planet passes in front of the star and there's a dip in the light received. Blue are the imaging. So when they take a picture, like how they found this exoplanet with just taking a photograph. Yellow are microlensing, which has to do with gravity, and red is radial velocity, which is like a wobbling motion happening in the star. What's really important about this is where B Sen ABB is on this graph. So it is on the plot, it has an unusually low mass ratio to the central system it's orbiting relative to the other detected planets in the imaging population. So what that means is that there is a ratio of mass of the planet to the star, how massive the star is. And you can plot it and you tend to get groupings of detection methods that are associated with a certain ratio and also how far away the planet is from its sun. So you can see most of the transit detections all lay within a certain range of planet to host star mass ratios and are all in a certain place in their orbits. And same with the radial velocity, you kind of get 2 groups. microlensing, you kind of get one. And then imaging is kind of scattered, but it looks like B Centauri AB is in a much different spot, in a very odd spot. So that is just something that I found particularly interesting, is learning about and seeing that maybe we might have to rethink our predictions on where exoplanets could be, around what stars they could be orbiting, because this planet itself doesn't fit in with the trends that we had before. And so the scientists in the team were looking at a lot of different things, why this is happening. And so they were trying to determine how the planet may have formed. And so they started looking at the orbit of this planet. And the properties that it has in its orbit don't indicate a violent past at all. Instead, they indicate the opposite, that the planet formed close to where it currently is in its orbit, with little to no orbital evolution at all. So its orbit didn't change much during formation whatsoever. It's kind of stayed in the same spot, so they think. Regardless of how it formed, though, what this discovery means is that the previous upper limit that we had of the star having to be at most 3 times the mass of the sun to be able to have a giant exoplanet within 5 astronomical units, or about the distance of Jupiter from it, it can't be applied fully across the board, because now we have this pretty major outlier in that trend. So what this shows is that stellar systems, and maybe even stars up to 6 to 10 times the mass of the sun, can hold giant planets on much wider orbits. So this one is at 100 times the distance of Jupiter from its star. So it's about 500 astronomical AU from its planet. So it kind of throws a lot of our ideas into question. And now, hopefully we'll look at more things to try to figure out what exactly is going on with that. Why lettering M to O for spectral categorizing? Oh, that's from Harry, and that's referring to the spectral class. So this has to do with the naming convention that was taken on. And there's no super reason for it, other than it's like a historical reasoning. It's one of those things in astronomy that it just is, and we've just lived with it and keep it because it's what works. Really, it started with Wilhelmina Fleming, who devised a system to classify the stars based on hydrogen absorption lines in their spectrum. And the strongest lines were A, the next strongest were B, and so on until O stars, in which the hydrogen lines were really, really weak. But we learned later that hydrogen lines are not the best indicator for classifying stars, because if the star gets too hot or cold, we don't see the lines in the visible. We see them in different parts of the electromagnetic spectrum. And so in the 1890s, Annie Jump Cannon revised the system, just focusing on the A, B, F, G, K, M, and O. And so instead of starting from all over again, she rearranged the existing ones in order of decreasing temperature into the sequence that we have now. So it's a part of astronomy history why we have it that way. That's the end of our planets, which I'm still very excited about, but I wanted to do the last little bit about Comet Leonard. So this is the comet that you may have heard about more and more recently, but it was actually discovered January 2021 when it was by Mars. So it's been around for almost a year now, and just now it's reaching us. And it's going to swoop around the sun, kind of pass behind the sun and go through it, in early January 2022. But a big question is whether or not it actually will. So what's interesting about this comet is that it should be getting brighter as it approaches the sun. And this is something that is across the board for all comets, right? As comets come closer, because they are made up of various ices and some rock holding it together, like a really gross snowball. As it gets closer to the sun, all that ice starts to vaporize. And that produces the light that we see. We start to see through various mechanisms light. And so the more that's vaporizing, the more that's going on, and the brighter it gets. And so this Comet Leonard does appear to be getting brighter, But it's actually only getting brighter because it's getting closer to Earth, which also makes sense. Like as it gets closer to us, we can see it better. It's closer, we can see it, but it's not actually brightening as it gets closer to the sun. If you were to like keep the like normalize the distance and take into brightness that way with the distance just set as one thing, it actually seems to be fading. So it seems to be getting fainter than as opposed to getting brighter. And so that have scientists worried that it is going to break apart and it's going to disintegrate. And it's happened before. Some comets have that we've seen have broken apart shortly after they started fading, even as they were getting closer to the sun. So it is a possibility that this can happen. But really, we don't exactly know what is going on with Comet Leonard. There could be lots of reasons for a comet being fading. It could just be running out of material. Ice to vaporize is a possibility. It could be about to break apart, be nothing left to hold on to it, and so it might break apart. It could be getting ripped apart by a different amounts of gravity pulling on it. We don't really know. And if it does break apart, it's unlikely that we will ever know what the actual cause of it breaking apart is. So that had me worried, but as of December 7th, so just a few days ago, the comet was fine, well, as fine as it could be for a comet that might be falling apart, but it's still in like the proper comet shape. So it still has a clear nucleus, it's still holding itself together, but the fading is continuing. It hasn't stopped fading, it's still doing that, which is really weird. And the first sign that a comet is going to break apart is if it loses its ion tail. So a comet has two tails. It's got like the gas tail coming off of it. And then it also has an ion tail, which is like energetic particles. And so when it loses that ion tail, that's the first sign that possibly within an hour, the comet's going to break apart. But as for now, we can still see it. It's still in the sky. We just might not see it when it loops back around, which I'll explain after. So this is how to view the comet, and at least at our latitudes, mid-northern latitudes, for the next, at least until tomorrow. So it will be visible to the naked eye, but it is best to get a pair of binoculars because it's still quite faint. It'll be probably easier to see with binoculars. And up until the 12th, it will be in the pre-dawn sky, but you want to look at the eastern sky really, really low on the horizon. So it's best to have a very flat area where you can directly see the horizon and not much in your way, and looking pretty much due east. You want to look that way. And this is a sky chart from NASA that shows like how the comet's been moving throughout the sky as the days have gone on. After the 12th, it's actually going to be out of our view because it's starting to get closer to the sun in its orbit, and it will loop back around. And when it loops back around, it'll be able to be viewed in the western sky. So this is from December 14th to the 25th. We'll be able to see it about an hour after sunset. But you are again going to want to look kind of west southwest in between the two, and again very low on the horizon. It's never going to get very high, and so you want to make sure, wow, the sun just like came out of nowhere, and so you want to make sure that you're looking in that direction. A good way to find it starting is about an hour after sunset. You'll be able to see Venus. It'll be like Jupiter, Saturn, Venus starting December, well, it's now, but at December 14th, if you look at Venus and then go like down towards the horizon and kind of to the right starting December 14th, that's kind of about where the comet will be. And then after the 17th, it'll be kind of below Venus and to the left afterwards. So that's kind of how you're going to want to see this comet. That is if it reappears after it disappears from our view. Hopefully it doesn't break apart, but if it does, wouldn't that be a bummer? Hi, Pride, and we have a question from Harry again. What are the main goals or purposes for studying exoplanets when the distance is so great that sending the fastest probes would take many, many years? So the fun fact, in my office, the curtains are broken, and so I can't actually close them. So this is just, I tried before, and I just live like this now. The main goal of looking for exoplanets and studying them isn't so much because we want to send things there or necessarily because we want to go them. It's actually because we want to learn more about our own solar system, which I know sounds like counterintuitive, but it is because we don't exactly know how our solar system started. We have a lot of ideas and like a pretty strong theory of how we think it started with the protoplanetary disk, but a lot of it is finding if we're unique or if there are other systems just like ours. And so also studying exoplanets is to find out if the Earth itself is unique or if there are other planets similar enough to Earth. And so that is a large part of why, even though they're so far, we still want to learn about them, because you can also say too, like our solar system's already here. We do not know what will happen to our solar system necessarily. And so our best bet at figuring out what it could be, what could happen to us, is by looking somewhere else. So that is a big part of why we're looking for at other exoplanets as opposed to what we have now. Yeah, but that's it about Comet Leonard. Hopefully we're able to see it. Hopefully we get some good weather and we're able to see it. I have not been able to see it. Pre-dawn is too early for me, so I will perhaps wait until after it loops back around and try to see it if possible. Yes, so that's it. If there's any other questions, feel free to ask. Yeah, Michael is in the chat today, enjoying watching me as opposed to me watching him on my week off. So that is a different thing. Pride, I'm not sure if that's a question or not, if you have to look in the mirror to see, or if that's referring to Michael and I switching spots this week, but yes, it's been fun. Coming up here at the Space Center, heads up that our hours are going to be changing close to Christmas time. So keep an eye on that. If you would like to visit us, we do have some slight changes in timings coming up just for the holidays. And then in the new year, we're going to have some fun new events as we get into the new year with everything coming up. So keep an eye out for that as well. And as for night sky things that you can see currently, let me pull up my screen here. There we go. And I will share it. There we go. So for tonight, actually, given hopefully if we end up having a clear sky, you will be able to see Jupiter, Saturn, and Venus all together in the nighttime sky. So this will also be seen later on in the month with the Comet Leonard viewing, but it is quite awesome to see just like on a day-to-day basis. I saw it last night when I was leaving the Space Center, and it was really cool because Jupiter was like right above the moon. And it was just really, really interesting. And so, yeah, right after the sun sets, you'll be able to see Venus. It'll be the brightest of the three, especially bright. And then Saturn and Jupiter kind of in a line together. Very cool. They'll be in the southwest just after sunset. And Venus isn't going to be up for very long. It follows very close to the sun, but Jupiter and Saturn will be up for a bit longer. So that will be something you can check out for tonight. All right, sorry, I was reading the chat, but yeah, last night was amazing. So that's all I have to share with you all. still have about 5 minutes. If you have any questions, feel free to ask them. Otherwise, I will end the live stream and see you all hopefully next time. And hopefully it will be Michael and I together again, because I don't think it has been for the last couple of while. So we will see. I have a question from Pride asking, what is your favorite galaxy? I have to say, I do love galaxies. I find them all very, very cool. But I don't think I actually have a favorite, which is probably, I should probably get one. But I do like our own galaxy, mainly because we really have a vague idea of what it looks like. We can't go out and see it, which I think is kind of neat. But I do like it in general. I also really like, there is one galaxy who I don't think has a name. It just has a long series of numbers, but I think it's one of the dragonfly galaxies that has like not as much dark matter as it should, and it's very confusing. And so it is an odd little galaxy that's caused a lot of problems. And then there's another one that has the opposite problem. It has too much dark matter than it should, mathematically. And so those two would probably be my favorite. And I'm sorry about YouTube not sending the notification. That could have been me not knowing what I'm doing, or it could have been YouTube. But hopefully you can go back and watch it, Keith. It should be kept on our website, or on the YouTube channel, so you should be able to go back and watch it. Harry's asking about survey of asteroids and how exact and responsive it can be. So there is the Center for Near Earth Objects, and they keep track of all of what are called near Earth objects, which include comets and asteroids. And if they have a very specific set of criteria that they follow and what they use to classify as a near Earth object or a near Earth asteroid or comet. And if that visible object meets that criteria, they keep it on a list and they monitor it, and they anticipate its orbits for 100 years into the future. So that's about how good we can get with surveillance of that coming towards us around us. We can get within about 100 years, but even then those aren't entirely accurate, because the thing with asteroids and comets and objects, coming towards us, is that we can only use the data we have, and often we don't see these objects at all. Like, who knows how long Comet Leonard has been in our solar system, but we only saw it January 2021. So we could only work with what we have. So it's kind of a give and take situation. All right, well, that is time almost, just about. So thank you all for coming. Sorry, I've been completely washed out by the sun. I'm not sorry the sun is here though. I've missed it. So I'll soak it up as much as I can. And I hope to see you all next time. So take care, everyone.